tu3 Tunnel Construction Project. Drilling and blasting method. Blast holes are drilled into the tunnel face and packed with explosives for clearing out the tunnel rock. This is done in accordance with New Australian Tunneling Method, NATM. In the method, the tunnel engineer will inspect the geology of the rock mass after blasting to determine what kind of tunnel support elements will be used. The supports may include the use of steel ribs, wire mesh, shotcrete, rock bolt, and so on. With these support elements in combination, the disturbed stresses adjacent to the rock mass of the tunnel after excavation will rebalance, and a stable stress condition will be re-established. At the same time, the tunnel's stability and construction safety will be ensured by utilizing the measuring instruments with which to monitor the tunnel displacement in response to the blasting. The monitored data were used as a feedback to flexibly adjust the primary support system. Finally, the invert concrete arch and inner concrete lining were installed to ultimately complete the tunnel construction. Pilot tunnel construction. The official launching of the pilot tunnel of the tu3 Tunnel was July of 1991. Up to July 1992, a total of 522 meters was excavated using conventional drilling and blasting method. The monthly progress rate was about 42 meters. During this one-year period, the design and manufacture of TBM was completed. The pilot tunnel TBM was a double shield type that was constructed by the Robbins Company of USA, with an excavation diameter of 4.8 meters and a shield length of 10.8 meters. The total length of the TBM system may reach up to 188 meters, including the backup system in connecting with the shield head. It uses electrical motor and main power supply. The entire TBM system has a total weight of 720 tons, with a length of 1,080 meters. And during this time, the TBM had suffered 10 times of stoppages. The first 7 stoppages were all in the agrolite rock mass and primarily caused by the rock wedges suddenly falling when passing through the major shear zones or the fault zones, rendering the TBM inoperable. The largest water ingress during these 7 stoppages was 40 liters per second. The latter 3 times of stoppages were located in quartzite of Silong Sandstone Formation, which has a significantly different lithological character, with the accompanying ingress of groundwater reaching 185 liters per second. These setbacks were resolved by using a bypass tunnel, which circled in front of the TBM to either remove the rock debris or improve geological condition by grouting method. The first 8 incidents were handled relatively quickly, with the 9th stoppage taking 10 months. However, the 10th stoppage wasn't resolved until September 1996, after a delay of 7.5 months, and then the D&B method was used to replace the TBM excavation. At the same time, the TBM was moved to the already completed ventilation relay station for comprehensive repairs and refitting. A highly efficient HD90 drill was also added. At the time when D&B proceeded, TBM was also followed right away. In December 2000, the TBM resumed excavation in the pilot tunnel. Up to November 2001, a total of 542 meters were tunneled, with the best monthly total 168 meters, totaling a monthly average progress rate of about 109 meters. It was during this time that the tunnel suffered stoppages number 11 and 12 in April and August of 2001, which resulted in delays of 128 and 76 days. Due to the TBM's extended period of operation in the Silong Sandstone Formation, its rear gears and minor gears were worn and cracked, and if they weren't changed in time, could result in main bearing failure. This was a grave issue, and TBM was shut down on November 8, 2002, and a large rock cavern was excavated to remove the TBM cutter head and anchor it in the cave wall. A temporary track crane was used to install new ring gears, minor gears, and a cutter head replacement assembly. This work was very complicated, tedious, precise, and highly technical, and took 83 days. During operations on June 8, 2003, the pilot TBM was shut down by the contractor for inspection following a power surge. The inspection showed there was a cavern in front, and the contractor decided to restart the TBM and attempt to work through the inferior geological conditions. But after restarting the TBM, a large quantity of rock debris discovered in front, which caused the conveyor belt to fail due to overload. The contractor tried several times to remove the rock debris and attempted to start the TBM, but it was impossible to resume TBM operations. Thereupon, on June 10, 2003, work was begun to resolve the TBM's 13th setback, an operation that took 72 days. During the 18.7 months between the 12th and 13th setbacks for the pilot tunnel's TBM, a total of 3,376 meters were excavated for a monthly average of 256 meters. During this, at 1,221 meters, the tunneling was at the hard quartz site of the Silong Sandstone Formation. That resulted in severe damage to the cutting discs, with 323 discs changed within 8 months, with the most change in 1 month hitting 109 discs, with 13 changed in 1 day alone. The average tunneling rate in non-Silong Sandstone Formation was 378 meters per month, with the best rate 400.8 meters per month, and the best daily rate 24.7 meters per day, achieving the TBM's intended effectiveness. Vertical shaft construction. The Xueshan Tunnel has a total of 3 vertical ventilation shaft sets. After the shaft has reached the bottom, then the inner concrete lining on the shaft wall is installed from bottom to top. The steps include installation of permanent water drainage system, steel casting assembly, concrete emplacement, curing, and then after completion, continue moving upward. In order to ensure smooth excavation of the shafts, pumps must be used to force out the water from the wells that flows in from the joints in the rocks. Water seepage from the shaft walls not only affects work progress, but also affects the quality of shotcrete supports, and therefore ground pre-treatment with grouting was used to minimize water seepage and reduce pump load and improve the efficiency of excavation and support construction.